In this podcast, we're going to talk about reactions in solution. In most chemical reactions, we need to dissolve the chemical into a solution in order for it to react. An aqueous solution is when a substance is dissolved in water. Soluble salts will dissociate in water, while molecules will remain intact within solution. For example, if I take solid glucose and dissolve it into water, the glucose remains C6H12O6 and is now in solution. Notice the carbon, hydrogen, and oxygen stay together. Salts will do something a little different as long as they're soluble. Let's go through an example. When a soluble salt is dissolved in water, it will dissociate in water, which means break apart into its ions. For example, sodium chloride is made up of two ions, sodium and chloride. So when we dissolve that into water, it'll actually become one sodium plus ion and one chloride minus ion. That's an easy one because it's a 1-to-1 ratio. Let's look at one that's a little harder. Here is aluminum sulfate. You'll notice that there are two aluminums, and when this salt dissociates, it becomes two aluminum 3 pluses. Once again, it's really good to practice figuring out what the charge is on the ions within a compound. The other thing that's in this compound is sulfate, which is SO4. That's the other ion. And you'll notice that there are 3 sulfates in there. So because there's 3 sulfates in there, we write it out as 3SO4, 2 minuses. So when aluminum sulfate is dissolved into water, it breaks apart into 5 ions. 2 of them are aluminum 3 plus, and 3 of them are sulfate with a 2 minus charge. When we write out chemical equations that are solution-based, and we are given the physical states of the compounds within the chemical equation, we sometimes write these out as complete or net ionic equations. What you see up here is what we call a molecular equation. It has all the substances combined together, nothing's broken apart. The first thing we do when we want to find a complete ionic equation is we balance the molecular equation. You'll notice we put a 2 in front of the AgNO3 and a 2 in front of the AgI. And you'll notice now we have 1 magnesium on both sides, 2 iodines on both sides, 2 silvers on both sides, 2 nitrogens on both sides, and 6 oxygens on both sides. So it is balanced. Now what I'm going to do is I'm going to take each of the ones that are aqueous and I'm going to dissociate them into their ions. The Mgi2 will dissociate into 1 Mg2 plus and 2 iodines with a -1 charge. The silver nitrate will also dissociate, but notice we have 2 of them. So we will have 2 Ag pluses and 2 NO3 minuses. Let's go to the product side. The MgNO32 will also dissociate because it is aqueous. So it will break apart into 1 Mg2 plus and 2 NO3 minuses. The AgI is a solid, which means it is not in solution and it will not dissociate. So we write that out just like it is. This type of equation that has all of the ions dissociated and they're all present in the equation is called the complete ionic equation. But you should notice that there are some ions on the reactant side and on the product side that are exactly the same. You'll notice that there's an Mg2 plus on both sides and 2 NO3 minuses on both sides. These are called spectator ions. These spectator ions were not truly involved in the chemical reaction. They remain the same before the reaction as they did after the reaction. So we cancel those out. And what we're left with is 2I minus plus 2 Ag plus yields 2 AgI. I like to write it that the metal comes first, so I will switch the Ag and the I. Now you'll notice that we have 2 Ag plus 2I minuses yields 2 AgI. For the purposes of balancing the equation in this way, we will reduce it down to 1 coefficient for each substance. So I get rid of the 2's and it now becomes a 1-to-1 ratio for all 3 substances. What we're left with after we cancel out the spectator ions is something we call the net ionic equation. This tells us which substances truly reacted in our chemical reaction.